Hello, welcome to today's talk about ARM Trustzone. We're gonna talk about what is Trustzone, and we're also gonna demonstrate the Trustzone-M feature on this board NRF9160. Short introduction about me. My name is Anand. I'm an embedded system engineer. I'm exploring the world of embedded Rust. Um, and also I'm very much keen and I'm exploring the security domain and the embedded systems leveraging Rust. So let's get started. Talk about what is Trustzone. Trustzone-M is a feature that provides a secure execution environment for the applications running on the controller. It allows for a creation of two virtual processors that can be termed as a secure world and a non-secure world. So the applications running in secure world have access to all the resources. We can perform sensitive operations such as cryptography, um, secure key storage, and various other things. Whereas applications running in the non-secure world don't have any access to secure resources. Secure resources means secure memory, secure RAM, secure peripherals, etc. Okay. This is an overview diagram of how our secure mode and a non-secure mode looks like. Further down in the secure mode, we have thread mode and handler mode, which will divide both the sections into privileged and unprivileged. So depending on our use case, we can keep our sensitive data, for example, secure key, secure bootloader, in the secure mode with most privileged section. In the secure mode in unprivileged section, we can keep any data equalization code. For example, yeah, mm, anything which is dealing with secure peripherals, which is taking data from the peripherals, processing it, and doing further things. In the non-secure mode, in the privilege section, we can keep our embedded OS or the RTOS, which is very specific OS for the device. In the unprivileged section of the non-secure mode, where here is the place where we'll be keeping our user applications, and this user application will be having its own communication stack, and it will be dealing with all the communication related things, so that even if someone has the access to our user application, that entity will not be having access to our secure key storage and secure bootloader, right? Yeah, so we'll move forward. So yeah, these are the special instructions. Now, uh, Cortex M is the TrustzoneM for the Cortex M controllers have been optimized for very fast context switching and low power utilization. So in order to do that, we have removed the monitor mode, which was there in the Cortex A processor. And once this monitor mode is removed, in order to switch from non-secure to secure states, these three special instructions are being used. So how these instructions are being used, we'll see. The first is a secure gateway. This is used for switching from non-secure to secure state. And this is the first instruction whenever a non-secure program tries to call a secure function. Then BXNS, this is the branch with exchange to non-secure state. It is used by secure software to branch or return to the non-secure program. After creating a secure gateway and after doing its all the processings, when you want to return to the non-secure program, this instruction is used, BXNS. The last is BLXNS. This is very simple and straightforward. Whenever you want to jump or whenever you want to call a function from secure area to the non-secure area, this instruction will be used. We'll see more in detail how this instruction will be used in the background by our code, by Rust code. Execution flow example. So yeah, we'll start from the power on reset. So once the device is reset, everything is secure. every peripheral, every memory location, and every area is by default secure. So our secure bootloader will start. It will boot the device, and after that there is trust zone initialization routine. If you can see this, the second part is the trust zone initialization. So trust zone initialization will initialize the area of the memory, such as flash and RAM, to be non-secure. Like we can define this particular area in flash and this particular area in RAM will be non-secure area, and this much peripherals or this list of peripheral will be non-secure peripherals. So all these thing about initialization of secure world and non-secure world will be taken care by this trust zone initialization. There is one more area which is non-secure callable. So in order to make secure resources or secure functions available to the non-secure world, we need to define this area which is non-secure callable area. This area will be in the secure area, in the secure memory only, but that particular area will be accessible to the non-secure program as well. And we will see how that is done. So configuration of this memory security attribute is done via two hardware blocks, which is secure attribution unit and or implementation. This is IDAU, implementation defined attribution unit. In the case of NRF9160, we have SPU, system protection unit. So this is an overview architecture, or this is an overview diagram of how SPU is being controlling our implementation defined attribution unit in NRF9160. So SPU provides the register interface to control IDAU internally, which monitors access to the memory mapped devices such as flash, RAM, and peripherals. After accessing the secure attributes, every memory access, for example, read, write, or execute, is been checked by the memory security attribute. Is been checked for the memory security attribute. SPU and IDAU both works together to enforce this kind of restrictions. In this diagram, we can see the configured view of the flash memory. On my left hand side, we can see the flash memory, which is configured to be non-secure, secure, non-secure callable. On the right hand side, we can see that there is secure attribution unit. In our case, we will be using the system partition, secure partition manager, or SPU, for configuring these flash regions or RAM regions. So using the register blocks of SPU, we can configure whichever memory we want to be non-secure and non-secure callable. The remaining memory is by default secure. In this, we can see that the resources allocation for the non-secure state and the secure state. On the left hand side, we can see the non-secure state has access to some of the flash, RAM. It has access for some of the peripherals. System control block, it has its own system control block. It has its own MPU, SCB, SysTick, etc. On the right hand side in the secure state, it has access to, or it has view, or yes, it has access to each and every peripherals, each and every memory, each and every registers, each and every system control blocks and debugs and everything. So this is the basic difference between program which are executing in the non-secure state and programs which are executing in the secure state. Talking about the implementation, well, to start about implementation, it's clear that we need to have two different projects. So first is a secure project, and other will be dealing with the non-secure project. After power on reset, the code from secure project will be starting the execution. In that secure execution, we need to write our own initialization routine. That initialization routine will be responsible for initializing this flash memory to be non-secure callable and non-secure flash, and it is also responsible for defining the peripherals which we want to be accessible or which we want to be non-secure. and same is the case with the RAM. So this is the sure that we'll need two different projects. Now, in order to have the communication or have the linking between these two different projects, we have these two compiler attributes. What are these two compiler attributes? We'll see. So the first one is SIMC non-secure entry. This compiler attribute will be used by the function in the secure world, which will define the function as non-secure callable. That means the non-secure program will have access to these functions. So whichever functions in the secure world is decorated by this compiler attribute, those functions will be accessible to the non-secure program or non-secure world. We'll read once the definition also. Function in the secure world are decorated with this attribute to indicate that it is an entry point for the non-secure calls. Yeah. So the other is SIMC non-secure call. So this attribute is used by the functions in the secure world, which is going to call the non-secure program or which is going to jump to the non-secure program. So the first one is the entry point, and the second one, this one is SIMC non-secure call, will be the exit point from the secure world. We'll see these two compiler attributes now in action. So this is very important. We'll start from left hand side. We'll start from top right corner. A non-secure program has already been in the execution. So there we have two external functions, foo1 and foo2. These two external functions are being defined in the secure world. Now, how this linking is happening, we can see. The foo1 is defined defined in the secure world with the compiler attribute SIMC non-secure entry. That means this is the entry point for the non-secure program. Whenever the foo1 hits, it branches, as you can see in the bottom side of the right hand corner. Branch with link, it will call the secure gateway instruction. This secure gateway instruction will create a secure gateway, and then foo1 function will be executing. After foo1 is executed, we will branch to the non-secure code. That means we'll come back where the foo1 was called. In this way, these three special instructions are also been handled by these compiler attributes. So as I was mentioning, we don't have to do squat. We have to use these compiler attributes at proper position or at proper function call, and these compiler attributes will be taking care of all these three instructions. Now there is one more topic here, that is veneers. Now what are these veneers? Here in the diagram you can see in the left hand side the branch veneer address. Some linker scripts is linking thing is happening here. So the veneer provides a simplified interface to the secure world, allowing non-secure application to access the secure world's resources, like without directly having to interact with the hardware-based security features. Veneer is typically implemented in the assembly language and is designed to be small, fast, with minimal overload. You can consider a veneer as a communication block between secure and the non-secure world. And this all creation of veneer tables and linking these two secure and non-secure program is been taken care by our compiler. We don't need to have worry about anything. In the Rust, we'll be utilizing a beautiful crate, not a beautiful crate, a well-maintained crate, TrustzoneM tools. We'll talk about it once we get into the action. So yeah, it's time to get our hands dirty. Let's start. So let's look at the implementation now. So before the implementation, I'll explain you about the project outline. So this diagram I have created to have an overview of a flash memory map of our project. So our project, you can consider a simple bootloader split into two parts: secure bootloader and the non-secure bootloader. And secure bootloader will initialize everything, such as non-secure callable regions, non-secure regions, non-secure RAM, non-secure peripherals, and secure peripherals, and all those things. That initialization routine will be here in the secure flash. That will be the part of the secure bootloader. The part of the bootloader which is non-secure is just a function which is passing on the control to the user firmware. Like after initialization, when we call this non-secure function of the non-secure bootloader, it will just jump, or it will just pass on the control to the user firmware. Correct. So yeah, so NRF91 has 1 MB of flash. So we have divided that flash into this kind of memory map. So 0 to 2F000 we have secure region. 2F000 to 30000 we have a non-secure callable region, and beyond that everything is non-secure. Okay. Now this is the crate which we are using, TrustzoneM tools, to establish the linking between secure and non-secure project. So there is already secure runtime and non-secure runtime here defined by the developer, and he has also provided some tools to generate the bindings between secure and non-secure world. These bindings and these macros are nothing but which we have discussed in our presentation. Now let's see things in action. So this is the Rust boot project. Now this, if we talk about this, this will be complete a different topic of discussion. Here we'll only concentrate upon the bootloader and the firmware part, and how we have integrated the trust zone things here. So in the bootloader, we have two different folders as we discussed: secure and non-secure. Secure part has its own dependency. Non-secure part has its own dependency. We are pulling on. Let's look at cargo.ml file. So yes, Cortex MRT, Cortex M, Rust boot hal. You can ignore for timing, but yeah, TrustzoneM macros we are pulling in from the tools which I have showed you. Secure runtime we are pulling in from the tools, and some embassy related stuffs which we are currently not using, but this is I have included because my future goal requires these things. Some deferred formatting statements, and build dependencies. Same cargo.ml is for non-secure project as well. Just we are not using embassy stuffs here. Okay, let's look at our main.rs file of our secure project. So code will start executing from here after the power on reset. We'll take the peripherals. We'll initialize we enable the faults, bus faults, secure faults, and memory faults in the system control block. Then we start initializing our trust zone routing. In this function, we are just asserting what all flash addresses and RAM addresses which we have provided are valid or not. Once the assertions are valid, we are initializing the SPU. Now SPU has this all register block. I'll show you here. Yeah. So these are the registers available for SPU. So we'll be using flash region 0 to 31 permission register, and we'll be dealing with this secure attribute bit. Whether the secure attribute is 0 or 1, depending on this, that particular flash region is defined as secure or non-secure. Same is the case of RAM region. In RAM region from 0 to 31, we can define each RAM region as secure or non-secure. Okay, so here depending on our secure flash and non-secure flash which we have defined here, we will set the secure bit as secure, or set the secure attribute bit as non-secure. Correct. Same is the case for RAM region also. For RAM we have this register as flash region N. Oh, sorry. For RAM region, we have RAM region N. So here we are defining the RAM regions as a security attribute to be secure or non-secure, depending on the NSRAM regions which we have defined in the earlier phase. Once flash and RAM is defined, we are defining the peripherals also. So for peripherals, we have this register, peripheral ID, 0 to 66 peripherals are there, and all the peripherals have permission register. In that permission register, we can set this bit as secure or non-secure. So here peripherals are also initialized to be secure and non-secure. Again, the pins also we need to specify whether the pins are secure or non-secure. That is the GPIO port. So for the simplicity sake, we are defining, or for simplicity sake, each pin is specified or each pin is initialized as a non-secure pin. Finally, we are, since this is not a specific thing, we have to disable the SAU so that our SPU takes priority and initialization is done. Okay. Now if we come back to the place from where we have started. So this is the bootloader, the initialization function. These are its parameters. Initialization function is done here. After that, this is Rust boot specific thing. We are getting the instance of flash memory, or we are getting the instance of the flash memory controller, and then we are starting our Rust boot thing. Here, the code is verifying the integrity and authenticity of the firmware, which we are going to start. Will not go much detail into this because this is not the today's point of discussion. We'll see how the jump is occurring or how we are jumping to the user firmware. So I know for the point that our code will come here and it will call this HAL boot from function. We'll go here, we'll call the boot from the NRF9160. So this is our boot from function. This is the final function which will be jumping to the non-secure code. So as you can see, there is trust zone bindings here present. This trust zone bindings we have generated with the non-secure code. So in the build script of this thing, this is the build script. So this TrustzoneM tools which we have pulled in our cargo.ml file. So here we have pulled in the TrustzoneM tools part. Yeah, see this TrustzoneM tools we have pulled in, and using that tools we are generating the bindings. These bindings we are generating with the non-secure main.rs because we have to call the function from this file. Now, okay. Once the bindings are generated, those bindings are accessible for us in this way. We can include those bindings and we can call this function from that binding. Let's see where is the function in the non-secure code. Here is the function, the boot from function. This is the extern C function. And here, for just for the sake of convenience, I'm setting an LED to be high, and also I'm initializing UART, but I'm not using it for time being. It doesn't matter. Currently, I don't need a UART. I'll just initialize the LED, and finally, I will jump on to the firmware base address, which is provided. So this function, this jump function is defined here. It will initialize the vector table for the non-secure portion, main stack pointer for the non-secure world, and reset vector for the non-secure world. Once everything is initialized, we'll bootstrap or we'll jump to the non-secure firmware. One more thing I wanted to show you in these bindings, this TrustzoneM bindings which we are talking about, these bindings are generated in the build file. in the target directory. I just want to show you those bindings. Let us compile this so that we'll get some bindings generated. I'll open into the integrate terminal. We'll see cargo build release. Let's see. It's building. Some warnings are there. Yeah, we got the secure project ready. We'll build the non-secure project as well now. Non-secure and cargo build release. Okay, let's do it on the terminal instead. Okay, let it be here. At least I like this terminal. So secure project is built, non-secure is built. Now we have to build firmware also. So we'll go to the firmware directory, cd more firmware NRF9160 boot firmware. We'll build this firmware. Okay, firmware we haven't discussed. So in the firmware part, we have two firmware for a specific reason, but for time being, for simplicity's sake, we'll just have a look at only one firmware because it's doing nothing. It's just blinking the LED. We are getting the peripherals, initializing the peripherals, and we are just blinking the peripherals in the loop, infinite loop, for a particular time interval, and nothing else. The rest of the things are not being taken into consideration because this loop is the infinite loop. The control will not go anywhere else. Yeah, so firmware is also built. Now it's time to flash our firmware at exact location which we wanted. So that thing can be done from here. I'll use probrs CLI to download bin at particular base address. We have to specify the chip NRF9160 which we are using and the file which you want to flash. Oh, no connected probes are found. Sorry. I need to connect my device. Yeah, so the device is connected now. Also, I want to show you one more thing, the programmer view of NRF9160. So this is our device. Yeah, we'll erase all first of all. Erasing, and yes, everything is erased. Now we'll flash our firmware first. So firmware is flashed. Now if you want to read it, yeah, you can see the firmware is being flashed here at 0x4000 location with 202508 bytes. Now we'll flash the non-secure part first. So cd change directory to oh sorry boards bootloaders NRF 9160 non-secure. We will just do cargo flash -release NRF 9160 underscore XXAA. Okay, something is missing. We don't want this slash. Now what is missing? What is missing, bro? Okay, We'll try once again. Argo flash. Okay, flash. Release. Chip NRF9160_XXAA. Yes. So it's flashing. Yes, it's done. Now we'll flash the secure bootloader also. And same cargo flash release chip NRF9160. And on the board, I think I can see, not yet, but yeah, we'll wait. Yes, so flashing is done. Now I can see the LED is blinking. The firmware has been started correctly. I'll attach a short video after this presentation so that you guys can have a look. And the thing which I want to show you is the target, release, thumb, and build. And here we can see the bindings which we have generated. So if we go to rust-boot-hal, these are the TrustzoneM bindings which we have generated, and this code is being called when we say the TrustZone binding, and we are calling Bootform. So this is the code which is actually being called, and so see here we can see this the macro which we were talking about. This macro SIMC non-secure call. That means this function is going to call a non-secure program. So this macro, this function is being decorated with this macro, and so this function will be calling the non-secure function, the boot from function. So as we have discussed, these macros are present there. It's just that this TrustzoneM tool is generating or taking care of these macros for us. We just need to define or we just need to create the bindings for the non-secure project. And once those bindings are created, we can call this function. So that's it from my side. If you have any doubts or you have anything, you can contact me or these things. And yeah, scan this for the LinkedIn profile. And thank you very much for your time. See you next time. So this is our board, and if we do a reset, you can see the LED is blinking and one LED is continuously on. So the blinking LED is from the firmware, and the LED which is continuously on is from the non-secure bootloader. Once again, I'll do the reset. Yeah.